Okay, folks, so we're going to get started on the notes for Unit 4. We're going to do Unit 4.1. Unit 4 is going to be about nuclear chemistry or the chemistry of radioactive decay. So, Henri Becquerel, who is a French physicist, accidentally discovers radioactivity in 1896. Becquerel was studying a particular ore of uranium called pitchblende, and he found that that particular ore was fluorescent. It was glow in the dark. If you shined a light on it, it would glow. So he started investigating this, and one time he decided to see what would happen if he took a piece of this pitchblende and he put it in a drawer with a photographic plate. And he wrapped the plate in black paper so that there could not be any light that would get through the paper. And then he puts it in a dark drawer in a dark lab in the dark night and leaves it overnight. When he comes back, he finds that the photographic plate was exposed. There was a dark image on the plate where the rock had been sitting, even though the plate had been in the dark. So it was not exposed to any kind of visible light. Therefore, Becquerel concludes that this ore must be producing some special different form of radiation that he called an invisible radiation, something that your eyes could not see. And that was what was producing the image on the photographic plate. So you can think about this kind of as a drawing. It would look like this. He takes the piece of uranium rock, he puts it on this photographic plate, which was essentially like a piece of film back in 1896, puts it in this closed drawer in the dark. And when he develops it, he finds that some kind of radiation has produced an image on this photographic plate. And so he figures that this radiation of energy must actually be coming from something inside the rock itself. And it wasn't being affected by the temperature, by whether the rock was glowing in the dark because of light emission, the pressure, electric field, magnetic fields. It was something that was completely different and hadn't been discovered anymore before. So he decided to call these Becquerel rays because if you discover it, you get to name it. And today, this is one of the processes that we call radioactivity. Marie and Pierre Curie, who were graduate students with Becquerel, they studied this activity their entire life. And Marie Curie is the one who actually comes up with the name radioactivity. It was actively emitting radiation, so radioactivity. So this radioactivity, or what we now more often call radioactive decay, is when the nuclei of certain radioactive elements are going to give off what we call ionizing energy. So this ionizing energy, this radiation, is usually in the release of three major types of energy: alpha particles, beta particles, and gamma energy. There are some other ones, but those are the big, most important three different types of radiation. So anytime we're talking about radiation, we can describe it in two different ways. One, we can look at what we call the wavelength, and that's the distance or the length that it takes to go from the crest or top of one wave to the crest of the next wave. And we can also look at the frequency, which is the number of waves that pass a point in a particular amount of time. Usually it's 1 second, so we kind of call it, it's like a waves per second. So if you want to think about the relationship between wavelength and frequency, you can actually use yourself as a demonstrator. So if I take my hand and I trace a long wavelength, I see that I don't make too many of these wavelengths in a second. So if the wavelength is long, I don't see that wavelength as many times. if the wavelength is very short, I can take my hand and make a very short wavelength wave, and then it's wave, 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 wave. So these two things are what we call inversely proportional to each other. As the wavelength increases, I see the frequency is going to decrease. A long wavelength doesn't come by my face as often. A short wavelength, as the wavelength decreases, then the frequency is going to increase. We can also see that that's going to have to do with the energy of the wave too. The longer the wavelength, the lower the frequency and the lower the energy. The shorter the wavelength, the higher the frequency and the higher the energy. So you should on your notes packet have some waves to label the wavelength like we talked about before. Remember, wavelength is the distance from the crest or top of the one wave to the top of the next wave. And so you can pause this video and fill in the wavelengths for the 3 examples on your page. Okay, so radiation comes in a whole spectrum of radiation. There's the tiny little part of it that we can see, but there are a lot of wavelengths of radiation that are too long for our eyes to see, and a lot of radiation that is too short for our eyes to respond to. So going from the longest to the shortest forms of radiation, we start with the longest one being radio waves. Since they're the longest wavelength, they are the lowest frequency. And after radio waves, we have microwaves, yes, like the kind that cook food in the microwave. Then we have infrared radiation. And right after infrared, we get the red color of visible light. So visible light has the longest wavelengths of visible light are red, and the shortest wavelengths of visible light are violet light. So if you remember the colors of the rainbow, you can remember it by using Roy G. Biv: red, orange, yellow, green, blue, indigo, violet. Roy G. Biv. So the longest wavelength is red light, the shortest wavelength is violet light. And then after that, we get too violet for us to see it, which is why they call it ultraviolet light. It's too short for our eyes to see. Then we get X-rays. X-rays are used for medical purposes. That's what they used to do, X-rays, like of your teeth or your arm if you break your arm. And then we have gamma rays, which are the highest energy, shortest wavelength, highest frequency form of electromagnetic radiation. So some things that we do already know is we know that atoms are composed of 3 subatomic particles: protons, neutrons, and electrons. And so some things we should know. First, the number of protons is the atomic number, and the atomic number is going to define the element. Remember what you learned about isotopes. The protons couldn't change, the neutrons changed. Protons and neutrons are found together in the nucleus of an atom. And remember, the total number of protons and neutrons is the atom's mass. And atoms of an element can differ in their masses because they have a different number of neutrons, and those are isotopes. Some isotopes or nuclei are unstable, so they're going to decompose or decay over time. They spontaneously emit a certain amount of energy or particles. Usually those particles are going to be made of protons or neutrons because they're coming from the nucleus, or they're going to affect protons or neutrons because they're coming from the nucleus. These emissions are radioactive decay or radioactivity. And those unstable isotopes are called radioactive isotopes. At the end of a nuclear process, we should get a more stable atom that has a lighter mass. So different isotopes are usually identified with their chemical symbol and their mass. So you might see something like uranium-235. That's in your notes packet. The uranium-235, the 235 and the 238 are the mass of those isotopes because the atomic number can't change as long as it's still uranium. So it's a little bit of a shorthand notation. The other way you'll see these symbols written is this atomic notation, which is also called nuclear symbol notation. And in your atomic notation, which is a shorthand for keeping track of the protons and neutrons in the nucleus, the mass number is going to go on the top left. Remember, the mass number is the number of protons plus the number of neutrons in your atom. And the atomic number is going to go on the bottom of the left. And then just what's here in the middle is just going to be the normal symbol of the element like you would get off the periodic table. So the way I always kind of try to remember this is I use a little mnemonic ape man, like, Tarzan the ape man. The APE reminds me that the atomic number down here at the bottom is the number of protons in the nucleus, and it's also the number of electrons in the neutral atom. So APE, atomic number, is protons and electrons. The man part says that the mass number minus the atomic number, which is the protons, is going to give me the neutrons. And what's kind of cool about this atomic notation is that this is already set up to do the subtraction. You've got the mass number on the top minus the atomic number on the bottom, and that means I could just draw a line under it and I would have the number of neutrons. A minus Z gives me the number of neutrons. So remember, of course, the atomic number is the protons and the electrons. The mass number is a whole number, and it's the sum of the protons and the neutrons. So let's try practicing a couple of atomic notations. For example, the carbon-14 isotope, which is used in radiocarbon dating. We use it to estimate the age of something that was once alive. So we remember that we're going to look at the periodic table. We're going to look at the periodic table, and there's a whole number in the box for carbon. It's not 12.01. That's the average atomic mass. We want that number 6. That's my whole number, no decimal points in the box. So the atomic number is right off the periodic table. For carbon, it's 6. For the mass number, remember I get that right after the dash in my notation. So the mass number is 14. So I would write the mass number on the top, 14. I write the atomic number on the bottom, 6. And of course, the symbol of my element is C for carbon. So that's my carbon-14 atomic notation. And since the mass number on top minus the atomic number on the bottom gives me the number of neutrons, I just have to do 14 minus 6. And that gives me my number of neutrons. That's going to be 8. So I have one more example here. The potassium-40 isotope is used to estimate the age of rocks. So we want to write the atomic notation for potassium-40. Again, we're going to pull out our periodic table and we're going to find the whole number in the box for potassium. Potassium is atomic number, sorry, that should say potassium there. The atomic number of potassium is 19, and the mass number is after the dash. So we would write it as 40 over 19, and then a K because that's the chemical symbol for potassium. And if I want to find the number of neutrons, I just do the mass number on the top. So 40 minus 19 gives me a 21 for the number of neutrons. So you've got some examples in exercise 3, and I thought we would look at a couple of them real quick, and then we'll go look at, you'll have time to look at your homework number 4.1. So I thought we'd look at these first two, argon 37 and uranium with the 238 up top. Remember, the mass number is either going to be the number after the dash. So for argon, it's going to be 37. Now I'm going to need a periodic table to do this because I have to look up what is the atomic number for argon. So I'm going to grab out a periodic table and I'm going to look for argon over here. So helium, neon, argon. And if I look in the box for argon, I see argon is element number 18. So that tells me the atomic number of argon every time, all the time, is 18. So I have 18 protons and 18 electrons. So now I do the mass number minus the atomic number, and that gives me the number of neutrons. So 37 minus 18 gives me my number of neutrons, which is 19. So those are pretty simple. But what if I have a symbol like this? I just have one number here, but it is at the top of my atom, which reminds me, remember the mass number always goes on the top of that notation. So my mass number here is going to be 238. And I'm going to have to pull out my periodic table and go all the way down to the bottom until I find uranium way down there at the very, very bottom. There it is, and it's element number 92. So that tells me that my protons are 92, my electrons are 92, and then I do 238 minus 92 to get my number of neutrons, which is going to be 146. So now if you flip over to the very back of your packet, you can see you've got homework 4.1, which is about these radioisotopes. And I do need to give you one piece of information on here. On the second row, the mass number, notice it's on the second row, it has an atomic number of 24. Will you please write in that the mass number is 51? So atomic number 24, in the box right next to it, put 51. And that way you'll have enough information to do that problem. If you don't put in the 51, you won't have any way to get the number of neutrons or to find a use. So what you want to do is you want to complete this table at the top. Use your resources on the internet to look up some uses. You don't have to get super detailed. You know, if it says that it's used in medical testing, you can just write that it's used in medicine. Or if it's just really bad for you to have around, you could write that it's a health hazard, something like that. So look up those uses. You're just going to fill in problem number 1, just that table at the top. And we'll get into the nuclear reactions in our next set of notes.